Welcome to the Chemistry, Biology and Math Revision Hub. Today we are going through the Pearson Edexcel potential questions for IAL Chemistry Unit 4. I'll begin with the first topic. Topic 11 is kinetics, and some of the sample questions that can come from this topic are: number 1, determining the rate of a reaction. This could be by collecting a specific volume of gas that has been obtained and within a specific period of time, so that the rate of that reaction will be change in volume, or the volume of gas collected, divided by the time in which that gas volume has been collected. In this case, the gas can be collected using a syringe, or we can use a measuring cylinder that is inverted over water, and then we can measure the rate of this reaction by dividing the volume of gas collected within a specific time to give you the rate of a reaction. We could also use change in mass of the reacting contents. In this case, a reaction will be carried out and the contents will be placed on a balance so that the decrease in mass will be measured, the gas will escape, and the change in that mass will be detected within a specific time. And you can use that to find the rate of a reaction. Another method could be measuring the change in concentration of reactants or products. This could be change in concentration over change in time, and this can be carried out by titration. However, most of the time before you titrate, you will need to quench using either ice-cold water, or sometimes they use a reagent like sodium hydrogen carbonate. So then you can titrate using a suitable indicator to get the concentration of any component, either reactant or product, within a specific time. And lastly, we can use change in color, or what we call colorimetry. In this case, the color intensity of the reactants and the products is going to be monitored, and if there is no more change in color, we can determine that the reaction has stopped so that we can find the rate within a specific time. Please remember that bromide, iodide, and chloride ions are not colored, while bromine, chlorine, and iodine could have specific colors. Here they could ask you to write the rate equation, find the order with respect to reactants, and the units of the rate constant. You can calculate the rate equation by saying rate is equal to the constant into the concentration of the reactants. However, we also have to find suitable orders with respect to each reactant. Remember that orders can be 0, 1, or 2, and the overall order of a reaction is the sum of all the orders of the components that appear in the rate equation. They could ask you to use the continuous method to determine the orders and ultimately the rate equation. In order to do this, you will have to draw a concentration time graph, and then from the concentration time graph, you will determine the half-life for the different reactant concentrations. If the half-life is constant, then we can assume that this is going to be first order with respect to that corresponding reactant. And then if the half-life doubles with progress of the reaction, then this is going to be second order with respect to that reactant. So on this note, you need to remember the shapes of concentration time graphs of 0 order, first order, and second order. You also need to remember the rate concentration graphs with respect to a reactant that is first order, 0 order, or second order. Finally, you need to know the rate against concentration squared graph. This is the graph I'm talking about. This is a rate versus concentration squared, and this is going to be a straight line through the origin. So let's continue. They can also ask you to find the rate of reaction at a specific time. So to do this, you need to draw a tangent at that specific time and find the gradient of that tangent. That gradient will be corresponding to the rate of reaction at that specific time. Another common question is the initial rate method. Here they can give you a table of results, and they can ask you to use the data to find the orders with respect to a specific reactant and ultimately write the rate equation. To do this, you have to keep a concentration of a specific reactant constant as the concentrations of the other reactants are varied, and then see how that affects the rate of a reaction so that you can be able to know if it's 0 order, first order, or second order with respect to that reactant. This question is very, very common. You have to go through the past papers. The next part, you have to understand reaction mechanisms and rate determining steps. Remember that reaction mechanisms are a series of elementary reactions that show steps which reactants go through in order to produce products. You need to revisit page 17 and understand about the iodine propanone titration method. These questions are very common in multiple choice questions where they give you the mechanism and the rate equation and ask you to choose which specific mechanism suits the rate equation. So if you have time, please visit question 7, unit 4, January 2021. It was a very good question on this topic. To continue next, they ask about catalysts. Now remember, catalysts can be homogeneous or they can be heterogeneous. You need to visit reactions on page 20, IAL chemistry textbook. You need to know how homogeneous catalysts work. Remember, some of these catalysts work in redox reactions whereby the catalyst can be oxidized in the first step of the mechanism, and then in the next step it's going to be reduced to go back to its original state. Or it could be reduced and then oxidized, like you see in iron 2 and iron 3 when they're used as homogeneous catalysts in the reaction between peroxide sulfate and iodide ions. This reaction is very common. Please remember to revisit that reaction. And remember that the reason as to why they use a positively charged catalyst is that two reactants are negatively charged and they repel each other. And again, to further emphasize, peroxide sulfate is negatively charged, iodide is negatively charged. If they are to react with each other, the reaction is going to be very slow because they will repel each other. So in order to fasten up this reaction, a positively charged catalyst is going to be used. Please revisit that page and fully understand the steps of these reactions and how these homogeneous catalysts work. You could also look at the free radical substitution reaction, whereby you produce radicals and then the radicals can take part in reactions when they are acting as homogeneous catalysts as well. If we go to heterogeneous catalysts, again, this is page 20 of your IAL textbook. You need to know how heterogeneous catalysts work. Remember, the reactants adsorb onto the surface of the catalyst. A reaction occurs on the surface of the catalyst requiring lower activation energy, and then the formed products are going to dissolve off from the surface of the catalyst. An example is iron acting as a catalyst in the formation of ammonia. Many past paper questions have asked you to compare and contrast between homogeneous and heterogeneous catalysts, and I have seen 6 more questions asking about this, so please ensure that you can know how to compare and contrast. And again, if a question came asking you to compare and contrast, compare is talking about the similarities and contrast is talking about the differences, so ensure that you can do that. Finally, about catalysts, they can ask you about autocatalysis, like the reaction between ethane dioic acid and manganate, in which the product, manganese 2, acts as a catalyst for this reaction. I recommend that you remember how the shape of a reaction that is autocatalyzed looks like. Finally, they can ask about Arrhenius equation. Please remember how to use this equation in drawing a curve of natural log of k against 1 over t. Arrhenius equation forms an equation in the form of y is equal to mx plus c. This is going to be a straight line graph with a negative gradient. The gradient of this line is negative Ea over r. So we can use the gradient of that line to give us the activation energy. So many questions can give you the data for the K, which is the rate constant, as well as the temperature, so that they can ask you to use the data to draw a graph. So ensure that you can convert K into natural log of K. So you will put 2 extra columns, one for natural log of K and one for 1 over T, and then use natural log of K versus 1 over T to draw a graph, which will be a straight line graph, whose gradient will be negative Ea over r. We could use the gradient of that line to calculate the activation energy for that specific reaction. Please remember this question is very, very common in most past papers. It could come in Unit 4 as well as Unit 6. Another thing that could come in Unit 6 is the initial rate method, where they ask you to be able to find the order with respect to a specific reactant, and definitely the rate equation that could come as well. So this is the end of topic 11. Let's continue to topic 12. From topic 12, which is entropy, they can ask about enthalpy level diagrams of exothermic and endothermic reactions, so ensure you fully understand those. They can ask you about the difference between thermodynamic stability and kinetic stability. We also need to know why some endothermic reactions can occur spontaneously at room temperature. They could ask you to explain entropy in terms of distribution of energy among molecules. On this same point, I wrote a key fact here. Mostly this is in multiple choice questions, whereby they give you maybe 3 or 2 different substances, all of them in gaseous state, and they ask you which one has the greatest entropy. The key thing here is to look for the substance that has the greatest number of electrons. That will be the one with the greatest disorder, and therefore the greatest entropy. They could ask you to state the second law of thermodynamics, which is stated in your textbook on page 35. And this says that in a spontaneous process, total entropy always increases. Please emphasize it's total entropy and not just entropy. Now, the most common questions on this topic are, of course, calculating the change in entropy of the system, change in entropy of a surrounding, and using those two to calculate the total entropy change. Please ensure that you fully understand this because this is a very common question. And on this note, you need to remember that the units for entropy are joules per Kelvin per mole. So if you're calculating the change in entropy of the surroundings, you need to convert the delta H units, which are just kilojoules per mole, into joules. So you multiply the value of delta H by 1,000 in order to convert it to joules instead of being kilojoules. So many students make this mistake. You have to ensure that you multiply the value given as delta H by 1,000 before you substitute it in calculation for the change in entropy of the surrounding. They could ask you to predict spontaneity of a reaction using change in entropy. Since we know that the S total should be positive for a reaction to be spontaneous, it means when the S system is positive and the S surrounding is positive, then of course that reaction is going to be spontaneous. They could ask you for an explanation for spontaneity of processes in changing state, or they could ask you reactions involving change in number of moles from reactants to products. They could ask you about lattice energy and Born-Haber cycles. Of course, in any unit for paper, be well assured there is going to be a question about calculation of entropy, whereby they ask you about entropy of the system, change in entropy of the system, change in the entropy of the surrounding, and delta S total. Or they could ask you about Born-Haber cycles and lattice energy calculations. So one of these is either going to come or both could come, but most of the time it's one of them. So lattice energy and Born-Haber cycles, they could ask you the factors affecting the magnitude of lattice energy. You need to ensure that you fully understand those. Explaining why some ionic compounds have a higher experimental lattice energy than the theoretical lattice energy. To explain this, you have to ensure you fully understand polarization, charge and size of the cation as well as the anion. Remember, for the cation to have greater polarizing power, the size should be smaller and the charge should be high. So please refer to polarization in order to explain the difference between experimental and theoretical lattice energy in ionic crystals. They could also ask you about calculations involving Born-Haber cycles. I recommend that you fully understand about lattice energy, first or second ionization energy, electron affinity, and so on, and how to label them on Born-Haber cycles. You also need to understand calculations involving enthalpy of solution, hydration energy, and lattice energy, because if a question came on lattice energy and Born-Haber cycles, be well assured this is going to be the whole package. And if a question came about entropy, this is going to be the whole package, asking you to do these calculations here, as well as some simple basic explanations relating that. For any unit for paper, you must fully understand this part here, and you must fully understand this part here, and this basic information here in order to pass any question. These questions are quite easy. They're easily predictable. If you practice with many past papers, you're well assured to get full marks on this. But you have to make sure you practiced enough. So let's continue to topic 13. Topic 13, equilibrium constants Kc and Kp. In the exams, questions about Kc will ask you to write equations for the equilibrium constant, and in this case, we'll be using the concentration terms at equilibrium. They can ask you equations involving homogeneous reactions, where reactants and products are in the same phase, or for heterogeneous reactions where reactants and products could be in different phases. So here what we have to do is you have to know how to calculate the initial concentration as well as the concentration as equilibrium is reached. Remember to ignore the concentration of the solid. So have to know how to calculate the units for the Kc. For equilibrium constant Kp, again here they'll ask you to write equations for the equilibrium constant. And since this is to do with partial pressures of gaseous reactants as well as products, we need to find out the initial moles as well as the moles at equilibrium. We also need to know how to calculate the partial pressure using mole fraction and the given total pressure. Then we can use the calculated partial pressure to calculate the Kp. And again, we need to know how to find the units for the calculated Kp value. Other questions on this topic can ask you about the factors that affect the equilibrium constant. They could ask you about effect of changing temperature on the equilibrium constant. Also know that increasing temperature shifts equilibrium to the endothermic side of the reaction, while decreasing temperature shifts the equilibrium to the exothermic side of the reaction. For an exothermic forward reaction, increasing temperature shifts equilibrium to the left, and therefore the equilibrium constant will decrease. And for an exothermic forward reaction, decreasing temperature will shift equilibrium to the right, and the equilibrium constant will increase. Also, for an endothermic forward reaction, decreasing temperature will shift equilibrium to the left, and the equilibrium constant will decrease, while for an endothermic forward reaction, increasing temperature shifts equilibrium to the right, and the equilibrium constant will increase. So you need to know how temperature affects the equilibrium constant, and this question could come mainly in section A as well as section B. The next is the effect of changing pressure on the equilibrium constant. Actually, you should know that change in pressure has no effect on the equilibrium constant. So here, when pressure is changed, the quotient QP will no longer be equal to KP, so the equilibrium will shift either to the right or to the left until the QP is equal to KP. So here we can say that KP was not affected, since at the end, the quotient QP will be finally equal to KP. So overall, there is no effect on the equilibrium constant when pressure is changed. They can also ask the effect of changing concentration on the equilibrium constant. Also, we know that concentration change has no effect on the equilibrium constant. However, when the concentration is changed, the quotient QC will no longer be equal to the equilibrium constant Kc. That means the position of equilibrium will be shifted appropriately or inevitably either to the left or to the right until the quotient QC is equal to the constant Kc. So overall, we will say that Kc was not affected, since in the end, the quotient QC will be finally equal to Kc. So if you want to revise this fully, you can visit page 67 to 69 and look at the sample calculations there. Lastly, we need to look at the relationship between total entropy change and the equilibrium constant. Remember the formula for linking total entropy change, where we said ES total is equal to R natural log of K. So again, here you need to revisit any equilibrium reaction that has color change, like the dinitrogen tetroxide as well as nitrogen dioxide. We know that the dinitrogen tetroxide is colorless while nitrogen dioxide is brown. So they could ask an equilibrium similar to that, and they ask you if these conditions are changed, what will be the color observed in the reaction mixture. Also, you need to remember the graph of entropy against percentage of components in an equilibrium mixture. This could be a section A question that could come. It's rare, but it could be asked, so focus on that as well. This brings us to the end of most questions that could be asked from topic 13. Let's continue to topic 14. Topic 14, acid-base equilibria. My experience, I think this is the hardest topic from Unit 4, and students have to handle this really, really carefully. So, from topic 14, they could ask you about acids and bases, identifying acid-base conjugate pairs from a reversible reaction. This is common in section A, the multiple choice questions. You also need to remember what is monobasic, dibasic, tribasic in terms of acids, and monoacidic, diacidic, triacidic in terms of bases, although these are not that common. You are required to know the substances that act as both acids and bases are amphoteric. You also need to understand that strong acids fully dissociate. Acids like hydrochloric acid, they go through full dissociation, and weak acids will dissociate partially or reversibly. The next part that can be asked is about pH calculations for strong acids. We know that pH is equal to the negative log of hydrogen ions, but for strong acids, we know since they dissociate fully, it means the concentration of the acid given is going to be the concentration of the hydrogen ions. So for strong monobasic acids like hydrochloric acid, the concentration of the acid is equal to the concentration of the hydrogen ions, and you can directly use that to find the pH. For strong dibasic acids like sulfuric acid, the dissociation can take place in phases. The first dissociation, losing the first proton, is going to be full dissociation to produce HSO4 minus. However, to convert HSO4 minus to SO4 2 minus, you will need to go through a reversible reaction in which the Ka for that has to be given so that you can find the pH of the specific acid. They could ask you to calculate pH or Ka for weak acids. For weak acids, we know that dissociation is not complete, so you need to practice writing the expression for Ka of a weak acid. The most common weak acid is ethanoic acid, and you need to know that ethanoic acid dissociates into ethanoate ions as well as H+. You need to learn how to make the hydrogen ion concentration the subject from the Ka equation. And also you need to learn that in this calculation, to make the hydrogen ions the subject, two assumptions are made. The first one is we assume that the initial concentration of the acid is equal to the equilibrium concentration of the acid. That means that the dissociation was so small so that the concentration of the acid did not change while equilibrium was reached. Also, you need to know that the hydrogen ion concentration from the dissociation of water is negligible in the calculation. So please remember to practice using Ka values to predict strength of an acid. A large Ka value or a smaller pKa value shows greater dissociation and thus a stronger acid. They will ask you questions about the ionic product of water, Kw, so please practice using Kw to calculate the pH, as done on page 87 of your textbook. You also need to put great emphasis on the effect of dilution on pH of weak as well as strong acids. Remember in your textbook they say with every tenfold dilution, the pH of a weak acid increases by 0.5, while the pH of a strong acid increases by 1. However, pH can never be greater than 7 on dilution, so you need to know that. You also need to remember that the pH of pure water decreases with increase in temperature due to the dissociation. So the higher the temperature, the higher the dissociation of pure water, the more the concentration of hydrogen ions released, the lower the pH. However, the acidity is not going to change since with every dissociation, the hydrogen ions released are equal to the hydroxide ions released, so it's going to remain neutral. You also need to learn how to draw acid-base titration curves. You also need to show clearly the buffer region on these graphs. You need to learn about the equivalence point, the half equivalence point, as well as the end point. And also you need to remember the calculations involving choice of an indicator on page 93. Lastly, they will ask about buffers. You need to remember the definition of a buffer. You need to work hard on the pH and Ka calculations for buffer solutions. You also need to remember how a buffer works when small amounts of acid or alkali are added. And again, in a buffer solution, when small amounts of acid or alkali are added, the quotient, which is the concentration of the acid divided by the concentration of the salt, is not significantly changed, and therefore the pH of that buffer solution will not be significantly changed, or we could say it remains almost constant. They could also ask questions about the half equivalence point, so please remember at half equivalence, pKa is equal to pH. The key point about questions from topic 14 is that you need to focus a lot on buffer calculations, pH calculations, calculations involving Kw, as well as calculations that require you to find Ka if the pH as well as the concentration terms are given. For you to get an A star in Unit 4, you gotta know topic 14 fully because many students find it really, really hard. This brings us to the end of potential questions that could come from topic 14. Let us continue to topic 15. Topic 15, carbonyls, carboxylic acids, and chirality. Remember that optical isomers have a chiral center and they are non-superimposable mirror images of each other. They could ask you to explain the effect of optical isomers on plane polarized light. Remember again, some optical isomers rotate plane polarized light to the left or anti-clockwise, and the others can rotate it to the right or clockwise. You need to fully understand what racemic mixtures are and how they affect plane polarized light. You need to know the mechanisms of SN1 and SN2 reactions and how they lead to formation of optical isomers. Please focus on page 112 and page 113. It's very important that you understand this, you understand that, as well as identification of optical isomers. Another common question comes from carbonyls. They could ask about their physical properties like the boiling points and the melting points in terms of the intermolecular forces of attraction that they could form. Please remember to count the number of electrons if it's a comparison so that you know if they have the same strength of London forces. They could ask you about reduction of carboxylic acids as well as oxidation of carbonyls like aldehydes. Remember the test for presence of a carbonyl group? We use 2,4-DNPH. You need to fully understand redox reactions that are used to distinguish between aldehydes and ketones. You need to know the observation with Fehling solution, Benedict's solution, Tollens reagent, as well as acidified potassium dichromate. These are all redox reactions. They'll be interested in the observations as well. The iodoform test is very common. You need to know a yellow solid is observed due to formation of triiodomethane. You need to know that this test could be positive for secondary alcohols with a terminal methyl group because iodine can oxidize the alcohol into a ketone, and then the ketone will give a positive test with the iodoform test. You need to know about nucleophilic addition reactions and mechanisms involving KCN and HCN with carbonyl compounds. This is very, very common. It comes a lot, as well as this distinguishing and reaction with 2,4-D and pH. Those come a lot. You need to know an explanation for the formation of rest-mate mixtures in the KCN-HCN reaction due to the planar carbonyl carbon. When we go to carboxylic acids, you need to know the explanation for the physical properties of carboxylic acids, like why their boiling and melting points are higher than those of alcohols as well as carbonyls with the same number of carbons. You need to know the preparation of carboxylic acids by acid and alkaline hydrolysis of nitriles. This is very common. You need to know it could be useful when you are going through synthetic routes. Reactions of carboxylic acids include reduction to primary alcohols. And again here, remember, yes, carboxylic acids can be reduced to aldehydes, but this reduction reaction is so fast, it goes through to primary alcohols, so the aldehyde may not be observed. So we usually say reduction to primary alcohols. Carboxylic acids go through esterification when they react with alcohols to produce esters. Carboxylic acids can go through halogenation in the presence of PCl5. The last reaction that carboxylic acids are involved in is alkaline and acid hydrolysis of esters. When you hydrolyze esters in the presence of an acid, you produce carboxylic acids, while in the presence of alkali like sodium hydroxide, you produce carboxylic salts. Next, they could ask reactions about acyl chlorides. This could come as well. Remember, reactions with alcohols to form esters. Acyl chlorides form esters, however, there is HCl that is produced, which could be toxic. So sometimes they ask you to compare formation of esters through reaction between alcohols and acyl chlorides, as well as formation of esters through a reaction between carboxylic acids and alcohols. So you need to know that, the advantages as well as the disadvantages of each method. They can ask you about reactions with ammonia and amines to form amides. When we go to esters and polyesters, of course, this is physical properties as well as hydrolysis reactions of esters that I've already talked about. Esters go through acid hydrolysis to produce alcohols and carboxylic acids. They also go through alkaline hydrolysis to produce carboxylic salts and alcohols. They can ask about condensation polymerization to form polyesters. Remember, polyesters are formed from dicarboxylic acids and diols, or they can be formed from diacyl chlorides and diols. Linking to this, you can be asked about chromatography. This could be common as well. It could be details about paper chromatography. You need to know how to calculate the RF factor, and using that to explain how you can be able to identify a specific compound. You need to know some brief details about column chromatography, GC as well as HPLC. In this case, most questions are focusing on the mobile as well as the stationary phase. They could also ask about spectroscopy. Here, they could ask about carbon-13 NMR or the proton NMR. In the carbon-13 NMR, to focus on the peaks as well as the chemical shifts, so please practice using chemical shift tables. With the proton NMR, you need to focus on the number of peaks obtained because those will show you how many proton environments are present. You need to focus on the peak area ratio because that could be useful in telling you how many protons are in each environment. You need to focus on the chemical shifts because they can help you in decoding the structure of the compound. And then the splitting patterns can tell you about the neighborhood of each specific proton in order for you to decode the specific compound. Now, questions about these peaks and so on can come in Unit 4 as well as Unit 6. So you need to practice using questions from past papers of Unit 4 as well as Unit 6. So this brings us to the end of these questions that could potentially be asked from Unit 4. Don't forget to subscribe. Bye-bye.